Thanks.
Time as any, Mr. Newman. Take her down to periscope depth.
Yes, sir. Clear the bridge. Dive.
Stand right.
And greetings, everybody. Welcome to the Evidence and Reasons for the Christian Faith video channel. I'm Salvador Cordova. Excuse me for the congestion. It's been a busy day. A lot of things happening. Tomorrow will be a debate, what they call a debate Armageddon on the Modern Day Debate channel. There'll be 12 hours of debate. And there are going to be 4 debates, so I presume that's going to be roughly allocated about 3 hours per debate. I'm scheduled at around 5 p.m., last I heard, to debate James Downard, a gentleman named James Downard, on the topic of, is there evidence for intelligent design? Now, he actually debated the topic with John Maddox about a year and a half ago or so, something like that. And I reviewed the debate, and James Downard said a few things that now, in light of James Stewart taking down Dave Farina, I don't think it's going to fly. And I feel like, just fair warning to him, I may call him on something he said. So let me try to bring that up. See if I can bring that up here. Now, please let me know if the audio is on the soft side. I haven't been able to adjust it yet. I ran out of time. And he's basically, it's just going to be a very short segment where he says all the pre-biotic nucleotides. So a nucleotide, for example, in our DNA, it's made of molecules called nucleotides. So those are the letters. You probably heard the letters of the alphabet of the DNA. It's A, C, T, G, or A, C, T, A, C, G, T, depending on how you want to collate it's 4 letters. And then for RNA, it's A, C, U, G. But in any case, he was saying that abiotic synthesis, the origin of life researchers, the abiogenesis researchers, have been able to synthesize all the chemicals. Now, some of you have watched the James Tour debate, and not debate, but his takedown of Dave Farina. Farina was just a mess. He said stupid stuff like it's very easy to synthesize any biomolecule. And then, of course, James Tour would grab this paper that showed how to synthesize a particular polysaccharide, and it was like a grand total of maybe 500 pages of characterization and recipe, and it was not easy. It made Dave Farina look like a real numbskull, honestly. And just for those who don't know, Dave Farina, I think he has a bachelor's in arts in chemistry, not even a bachelor of science. James Tour, on the other hand, one of the top chemists on the planet. So this was like a bulldozer running over a snail. I mean, it was just ugly. That being said, there are some subtleties, and please, those, especially anyone who's a chemist and who sees this in recording, if I say something wrong, please correct me, because I'm not a chemist. I know enough chemistry to be able to do kind of my work. Some of you saw the peer-reviewed article that I was pleased to announce today that I was co-author of. It's really more of a peer-reviewed press release because we were announcing some of the work that our team had been doing for the last 2 years, and we had presented at a poster session at the giant conference on experimental biology, and really that session was just kind of codified, and it had to go through the acceptance process that we could present because they don't want cranks just showing up and saying whatever. So this was a respected body, and we had, it felt like we had a bazillion co-authors. They're probably, they're probably like 7 or so co-authors, including myself. And I don't know how I got on that topic. Yeah, I know just enough chemistry to be able to participate in a team like that. My background is more varied in molecular biophysics and computational stuff. They've not had any use for my aerospace background yet, but maybe one biology team will find use for it. So if there are errors in what I say, I would be very grateful. If there are corrections. So James Tour just demolished Dave Farina, but I want to caution ID proponents and creationists, be careful about how you word what he says, because sometimes when he says the synthesis experiment fails, it doesn't mean that they didn't synthesize anything. What I very carefully listened to his discussion on the synthesis of nucleotides, particularly that of the carbohydrates, because a nucleotide, I'm going to show some pictures of this. It needs a carbohydrate known as a beta D2 deoxyribose for DNA or ribose for RNA, and it has to be the furanose form, very specific. And so it's not like this didn't get synthesized. It got synthesized in very low proportions, and I'll explain why. It had a lot of contaminants, so it wasn't pure. So when James Downard said we were able to synthesize, the abiogenesis researchers synthesized this, one could argue he is correct in the sense it did get made. James Tour would say it's still a failure because it wasn't insufficient quantities and purities. So I have to also watch my words carefully and say James Tour proved it, surveyed the literature, and he showed it wasn't synthesized. The proper term is it wasn't synthesized in adequate quantities and purity, and the process of purification is a major issue because of the issue of spontaneous isomerization. And I'm going to cover all that, because if I debate James Downard and he said, oh yeah, you haven't read the paper that it got synthesized, I have to choose my words carefully because I'm going to be in the debate. So I'm going to I can ding him by saying it wasn't in sufficient quantities and purity. And that's really important because that's important to the ID argument I'm going to be making about abiogenesis. So that being said, I'm going to play the clip from his debate with John Maddox. And I may confront him tomorrow night on his claim. And I'm going to confront him and say, the way you're representing this is not, it's not fair. It's misleading, and you need to come to terms with it, because if you're representing this as an advance, that it seems then that it's going to be adequate chemistry. That's just not right. And in fact, chemical mixtures that have come out of this would lend support that it would be astronomically infeasible, starting from the soups that were made by these guys, to form a DNA, the DNA we recognize, by the sort of chemical processes we would expect in a prebiotic soup. So I haven't adjusted the volume on this clip, but let me know if you can hear it. Otherwise, I'll just try to explain what he said. Let's see if I can get this thing going here.
Thanks.
Oop, wrong one. Sorry, guys. Let me try to get this going.
Other possible question about the origin of life.
Well,
Gotcha.
they may be dealing with a very different question. It is
a
the
really
fact
short
that
review.
at least over the last few years, it's become quite clear that all of the nucleotides that are used in evolutionary systems, the four ones that are found in DNA and the fifth one, uracil, that's used in RNA, can be generated quite naturally and inevitably in prebiotic context. Well,
Gotcha.
they may be dealing with a very different question. It is the
really
fact
short
that
and
at
pithy.
least over the last few years, it's become quite clear that all of the nucleotides that are used in evolutionary systems, the four ones that are found in DNA and the fifth one, uracil, that's used in RNA, can be generated quite naturally and inevitably in prebiotic context. There's been
So he's saying it's been shown over the last few years that all of the nucleotides that are necessary to make DNA can be generated in a prebiotic context. There is something misleading in what he said. He said it's natural and inevitable. But there's a problem he's omitting in something that James Tour highlighted. Now, again, I also have to kind of caution people, and if I were talking to Dr. Tour, I'd say, Dr. Tour, I think your choice of words could be improved. You have to say it wasn't generated in sufficient quantities and adequate purity. And let me explain where this is going, first of all. I'm going to do this by analogy, because if I go straight to the chemistry, it might just blow everyone away. And so, since the talk is going to be about a design argument, and I hope the computer doesn't blow up when I do this. Sometimes it does. Let me see if I can. I'm going to share my screen. So I want to be able to, I hope you can conceptualize. I've shown this picture before, but just to help you out, let's say we just have these quarters here, and they're in various orientations. They could be heads or tails. It could be heads or tails. And this is, now I drew this up. I didn't photograph it, but this is meant to simulate if we just throw a bunch of quarters and randomly toss them, there are about 55 or so quarters, into a little tray, it might look something like this. And if we shake it up or whatever, this is randomized. However, if we can arrange it in a way that it starts to look less random. And I'll explain how it is we know that it's less random. And I'll give some more proper terminology here. But we would definitely say that if we arrange the 55 coins this way, not only are they all heads, they're in nice rows and columns, and the head and George Washington's sculpture there is oriented all the same for all that. We would call this a state, if borrowing some terms from statistical mechanics and math and thermodynamics, we call this a state of low multiplicity. For example, being all heads, intuitively, we know that this is improbable as a matter of principle. And we would say that because it's a violation of the law of large numbers. This is a violation of the law of large numbers. If we just take the binomial distribution, we would say that random flips of the coin would generally be about 50% heads, 50% tails. The macro state of being 100% heads is a low multiplicity configuration. So you can look this up, and if someone wants references, we can do that. And I know James Downard will be demanding references. I'm just like, okay, James, this is really trivial, but if you insist, then I'll call his bluff here. I'll call his bluff. So we can call this improbable as a matter of principle. And we could also say the same for like it being in rows and columns, although the argument's a little harder. And then also for George Washington's head being oriented in the right way. So how does this relate to the chemistry? Well, for one, if we have a mix of nucleotides, let me turn this off. If we have a mix of nucleotides that are right and left-handed, say your synthesis experiments makes a heterochiral mixture, whereas DNA is homochiral in terms of the sugar, in terms of the deoxyribose, and for RNAs, the riboses. If it's all the D form, which is the right-handed, the dexterorotatory, something like that, the D form, it's all the D form, it's like being all heads. So biology has a feature of it at a very basal level that is like, okay, you can't just take a random mix that's kind of like half heads and half tails, and then expect random sets of events or chemical sets of events to assemble them to make an RNA or a DNA that has all the riboses or deoxyriboses in the D configuration. So I'm just going to take a timeout here. Is there any questions about, are there any questions here? I'll try to monitor the side chat about the concept of a violation of the law of large numbers. So, there are various ways. Let me see if I could bring this up again. So if we started with a mix of heads and tails, at the very least, there needs to be a mechanism that's going to sort this out. That is non-trivial. Everyone knows that. This is really non-trivial. This is a nasty problem. In fact, when we do synthesis of DNAs, say in Craig Ventnor's synthetic, so-called synthetic cell, we have to start off with purified ingredients because otherwise you'll get a mess. So let me try to show, see if I have a diagram of DNA here. I'm going to try to bring it up. See if I have my, oh, yes, it's right here. Hang on, apologies. I had it right under my nose. So in DNA, the sugar here is this, oh, I don't know what's, oh, I pressed the wrong button. This sugar here is the beta D, the beta D2 deoxyribose furanose. I know that's a mouthful. And I'm going to just show how improbable it is to pick that out. So these are all identical here. And in one of the experiments where they synthesized this, I'll show you the pool that they had to they had to start with. It was the Eschenmoser experiment. They have since tried to improve upon it, but there's still problems. In the Eschenmoser experiment, they got all of these forms here, all of these molecules, or most of the ones represented here. And what's not pointed out here, this is only a small sampling because, let's see, in life, in life, this is what you have to select out from a pool of all these contaminants when it was synthesized. From a pool of all this contaminants, you have to select this to make the DNA. So let me see if I can also, maybe I can duplicate a slide here to maybe highlight what's going on. So I'm going to duplicate a slide. See if it'll let me do this now. So what can't be done is we get what can't be done is we get this, and then in the next letter of this quasi DNA, it's this, and then we get this, or then we get a piece of this, and then also it has to be in the right orientation, etc. Because what we want is we only want this here, and it's always in the correct. You see, this molecule can actually be rotated, and that's not good. It has to be the right molecule and oriented in the right way, because you could actually rotate this and get it to connect funny. So let me look at the side chat here. Guys, can we not clog the side chat with talks about slavery? I am trying to conduct a scientific discussion, please. Can we not have a talk? Can you acknowledge that, please? Because I am trying to communicate some science here. I'd appreciate it. All right. So SpongeBob says, okay, so far so good. And I'm going to keep looking. All right. Seer Sunfish, I'm trying to communicate with the guys here, and if you could just take it elsewhere, I'd appreciate it, because some guys are actually trying to understand the chemistry here, and I'm being downvoted to death. Okay. So, all right, so we'll proceed here. So this orientation, we could actually then even make this analogy even stronger with the coins, because we could like use different coins and then different orientations and all, but I haven't gotten around to that. So let me try to explain. So what James Tour was pointing out, in the Eschenmoser experiment, they tried to synthesize this, and to a lesser degree, the Sutherland experiment, it made all these contaminants. And why does it make contaminants? And this is a serious problem for origin of life. Even if you start out with pure ingredients, the contaminants will spontaneously. This is the key. The contaminants are spontaneously generated. For those people with a little bit of background in chemistry, we have these equilibrium conditions, where their equilibrium concentrations of the various substances is going to get to a certain proportion. If you have something in solution, it's just natural, you can't help it. And so let me point out what happens in an equilibrium solution where you throw water. So if we throw, okay, this is the, I'm going to highlight the desired molecule right there. That is the beta D2-deoxyribose furanose form. So this is what's really crazy. When I showed you the diagram of all the chemicals, they all have the same proportion. They have the same number of hydrogens. All these molecules here, all these isomers, have the same number of hydrogens, oxygens, and carbons. And what's really bad is that they will normally interconvert to the other forms. So what do I mean by the isomerization, spontaneous isomerization? If hypothetically we started with just this molecule and it was purified and then throw it in water, it's going to spontaneously generate this molecule, this molecule, this molecule, this molecule. And what's worse is if we remove the water, all you end up with is these two molecules down here. These are called pyranoses. So these are all called D2-deoxyriboses, which would, when we usually say deoxyribose, we think of what makes DNA, and it's specifically this furanose form, this beta furanose form. But there's also the alpha furanose form, and then this linear form, and then the pyranoses. These are all valid deoxyriboses. And so if you try to purify the mixture by, say, removing the contaminants, what'll happen is what's left, if you supposedly have the good stuff, it's going to go and create all the contaminants again. It's going to create all the contaminants again. You can't just do the cleanup and filtration one time and then expect to have a clean mixture. This is a serious problem. So any questions there about the purification problem? Why the contaminants spontaneously emerge? This is going to be a problem for abiogenesis. So I'm just pointing out when Dr. Tour was talking about the synthesis experiments, he kept pointing out all the emergence of all these undesirable products. It's not a matter of them doing the experiment or the synthesis badly. It's just natural that you're going to get a lot of stuff you don't want because of this spontaneous isomerization. So just leaving the chemicals to themselves, it's going to create these contaminants. It's not the fact that you failed in your filtration or your whatever, trying to purify it. How do we get around this? Well, in life, we can get the whole molecule and it's a little bit more stable and it won't spontaneously isomerize, which helps, which really helps. And then so when we do our DNA synthesis experiments, we'll take something like the DNA with some added stuff on it to protecting groups or whatever. So let me show that. And this is kind of a good rehearsal here. So this is kind of the normal D form of the DNA. The B means the base. This is where you get the ACTG right here. So it has to be, once you add the phosphor group and then the nucleotide, and then you add what they call protection groups, it'll be stable. And that's what you start out with. The people who are doing DNA synthesis from scratch, like say they want to do genetic engineering, they have to buy the chemicals already pre-made, and it's not a trivial process to make it. I saw some of how they would try to synthesize these chemicals. They have to start with living things, extract it from living things, add some chemicals, filter it out, and it's stable. They're trying to prevent the spontaneous isomerization. And then it's a nightmare to be trying to connect this together piece by piece. So I'm going to challenge James Downard on this. I mean, if you're gonna say it, if he's going to make that claim, I'm going to point out that there are problems with that abiotic synthesis. It cannot be represented as a legitimate advance. And I'll point out the reason, because the mixtures are contaminated as a matter of principle. It's not that the chemists failed. This is natural that you're going to get spontaneous isomerization And my understanding is, and let me point this out. My understanding is the spontaneous isomerization will result in not being able to build this. At best, you're going to get just a mess of how these, see these sugars here, they will not be the same in every location. I don't know that you'd even be able to build a polymer. This would be such a mess. We can make estimates based simply on the law of large numbers and the binomial distribution, what the probability is that you can even make a DNA. We're not even talking about a DNA that has any useful recipe for a protein. We just want to have a string of DNA or two strands that make a double helix. It's just not gonna happen based on probability if you're starting off with basically a mixture that is a matter of principle contaminated. And there is a whole discussion on what happens if you start to, the term that Dr. Carter and friends use is it gunks it up. It gunks it up. So these are only some of the contaminants that happen now, would happen in the synthesis of just the riboses. But what if you have a contaminated environment to begin with? You have no idea what other chemicals are there. And so the improbability becomes worse. So this, again, you know, people will tend to trivialize this problem because, like, for example, let's just look at the coins. An intelligent mind, this is like child's play. I could tell a kid to make everything heads. It's trivial for him, trivial for an intelligence. Conceptually, we can think of just picking out a desired chemical out of a chemical soup and piecing it together. To do that in a random soup is not so easy. And even in the modern day, as Dr. Tour is pointing out, to be able to pick out the right one and put it in an orientation, he's talking about the difficulty of connecting parts. It's a nightmarish thing. That's why we need specialized enzymes to put this together. So I'm going to challenge James Downard on this because I feel that he kind of pulled a Dave Farina and imitated him, just spewing something that really wasn't correct. But in defense of, not that I would normally defend Dave Farina or James Downard, in a technical sense, they could be viewed as right. So the ID side, all they have to do is just modify the wording and say it did synthesize, but not in the adequate quantities and purification, because DNA requires to be made by that specific molecule that would have to be picked out of a mixture of spontaneously forming contaminants. And I really did understate how bad the problem is in this diagram, because this is just, you see it says D here, just double everything here that has, and put an L. So now you have even more of these chemicals, and this poor guy here is sitting in a mixture that see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It might be having 12. It might be having, like, say 10 undesirables, and then you double that number, it's 20. So out of a sea of 20, just for one trial, you have a very high probability of getting something that won't be the right one. And the right one meaning something that's the same as the prior one, just like flipping heads. Like, you know, in a sense, there's no right or wrong. What I'm saying is to be able to create a molecule with low multiplicity. And remember, all heads is low multiplicity. It could be all tails. That's low multiplicity. So hypothetically, we might pick a beta L furanose and make, make all the DNAs with a beta L furanose. But the idea is you're getting the same one consistently. And so that just becomes very improbable to keep rolling, so to speak, figuratively speaking, rolling the dice and getting the same number each time. And this is like what I already counted 20, but there's so many forms of arabinose, xylose, and lysose. The reason I know that is this is from Change Tan's book. Yeah, look at all the forms here. These are the deoxylysose. These are all the other forms that you're, and I don't think she even stated all of them. This would be a synthesis nightmare. So that's pretty much it. I'm probably have to get ready for my James Downard pre-show. Are there any questions? I just wanted to throw this out. Let me see. Let me see some of the questions here. First off, let me see if I can. Praying for you, Sal. My mother died in October. Blessings and good health. Understood there are side effects and time limits since the chemicals break down and not bioavailable. Thank you for your thoughts. Without you guys, I think this would be a really rough time. I can feel the strength of your prayers during this time of adjustment. And by the way, Gary, since your mother passed away in October, condolences to you. I totally understand what you must be going through, brother. Now, I was the primary caregiver for 18 years from really, especially the last 7, and that was really tough. Oh, and then Andrew, congrats on the publication, Sal. And so let's see, SF Mod did ask a question. I want to. We wouldn't actually need to, I mean, certainly a simulation could be run, but we could just use the law of large numbers and the binomial distribution. There is a program on StatTrak that does the binomial distribution. So you would just figure in the odds of success, given that I showed all these other forms. And the chemist would know, like, if it's only 1% of the time you get the one in DNA, and then you roll the dice again, and there's only a 1% chance you're going to get that one. And what James Tour pointed out is life is pick the harder one, the less probable one. Life is made of the least probable elements. So we wouldn't actually need to run a simulation, but it would be worth it to make a visualization so people can actually see conceptually what the problem is. That they could see that if they try to polymerize something like this, what a mess it could be. And some of the actual physical experiments have shown that you may get polymers that are just a total mess if you get a polymer at all, which is also another challenge. And there are a number of challenges with that because synthesis in a water environment doesn't work so well. You get hydrolysis rather than condensation reactions. And then if you try to do it in the dry state, that also has problems of its own. And my point is that how improbable does something have to be before you accept the chance that something is designed? At what point are you going to wager your soul on it, in other words? And I've framed this also in very personal terms by citing John chapter 9. I said, if Jesus healed you of blindness, would you follow him the rest of your life? A lot of people said no. I said, okay, that tells me what your threshold is for belief. And for some, it's like they'll never believe. Okay, so anyway, let me see if there are other messages. I'm in an argument at work about it. So I think the easiest argument is, and God made some of the probability, or there are more probability arguments to origin of life and evolution, biological evolution. I'm giving you the simpler ones. And that's why I like the ones with coins. Even a little child, even a little child will understand this configuration of coins is not particularly astonishing, even though it is technically improbable because you can't repeat it. But the little child, and I actually did this with the 6-year-old, he knew that this was special. He said, you touched it, you did something. He knew I did that. So let me provide some references. So for references, I'm going to cite this article. And we're having a thunderstorm here. I don't know if we might get whacked. So law of large numbers and binomial distribution. And if you want to throw the math in there, it's there. There's lots of nice math for James to go through. He wants to go through the math. We can do that. Oh, by the way, SF BMod, Joel, the reason I said we don't need necessarily computer simulations, it can be calculated with this. And there's also something called Pascal's triangle. Although the binomial distribution is more accurate, but part of the binomial, one special case of the binomial distribution could be represented by Pascal's triangle. And this will get to be an enormous triangle, like bazillions of, you know, we have 1, 2, 3, 4, 5, 6, 7, 8 in that particular row. You could have bazillions of elements. And so like the all heads configuration will probably be just, you know, you'll see a 1 here, only one configuration will be there. That's what we call a low multiplicity. And I covered that there. So, I mean, if James wants to go down that rabbit hole, it's like, yeah, you're just going to give me a chance to show some math. And maybe some people need that, because I've had actually, I've heard some numbskulls, and I'm sorry to, you know, I try really hard not to do name calling, but sometimes I get frustrated because I heard someone on a channel that which name I shall not mention, but then on also internet, in another internet discussion forum, they said the all heads configuration is not particularly improbable. I'm just like, okay, you may be correct if you're talking microstates, but not macrostates. But there was a 1.5 year discussion. They said, oh, that's not all that improbable. It's just an accident of our perception. I'd say nobody. You run this by a statistician, he's going to have issues with you. And it is, again, because of the low multiplicity. It's going to take some thought why that would just leap out at you. Okay, it's actually a little deeper than you think. And it's not a, it may look trivial that it's so obvious and intuitive and self-evident, but to actually demonstrate it mathematically requires a little bit of sophistication. All right, so I will grant that. But for them to say that this is not improbable as a matter of principle, that's when I say these guys are numbskulls. But I have heard them make that argument. So let me, oh boy, lawyers think math should be against the law. So I'm going to try to challenge James Downard on his claim. On the other hand, I did try to do my due diligence and review James Tour's evaluation of this. And technically speaking, it wasn't that they weren't able to make some stuff. It was that it wasn't in the appropriate sufficient quantities and purity. By purity, we mean really 100% pure. It has to be, that's very difficult to do. It has to be in the right concentration, because if you have very small concentrations and you have, it's just not going to form. So I just want to, you know, I feel some responsibility to try to train, to try to, as best as I can, to inform people how to make their arguments. Don't just say James Tour disproved that it didn't synthesize. It didn't synthesize with the right purity. If you can just say that with the right purity, which would mean 100% purity, then I think you're good to go. And so we'll see how this pans out in the debate, and I'm going to use the law of large numbers against Mr. Downard. So no disrespect to him. He's a very brilliant mind. I look forward to seeing how he's responding to this. So thank you very much. And I'm going to prepare for my next segment, which will be basically what I'm presenting to James Downard tomorrow. So I'll see you maybe in about 35 minutes. I'm going to have to postpone the next segment to later. So thank you very much. And I'll see you around 11 p.m. Eastern time. Thank you. Take care. And God bless you.